Stream. We're live. Hi, chat. Okay, so yeah, I guess hopefully things have improved. Unfortunately, I'm pretty busy, so I haven't spent any time figuring out how to make the chat more to make it easier to look at while I'm writing things on the screen. But here we are, so let's open up our textbook. Come to all these live streams ready to ask some questions and ready with the textbook open. And doesn't have to be this one, which is an open free textbook. Again, I'll probably put the link back in the description. It's on the description in the first videos, but of course you can use whatever textbook you're using for your class. So hopefully someone will have some questions about some stuff. This week, the class I'm TAing has moved on to stuff like matrix multiplication and determinants and elementary matrices. So maybe I'll talk about a few of these things. And then there's actually some more basic problems I wanted to go back and do some step-by-step solutions of. So maybe I'll do that afterwards. Yeah. So I'll open up a new page here. And what should we start with today? Well, let's talk about elementary matrices, right? So if we want to talk about elementary matrices, I mean, the best place to start is by going to our textbook, right? So I'm going to scroll down, find the relevant section in the textbook, well, probably under the chapter on matrices, elementary matrices, right? And so I want to go over again, because maybe you've gotten used to working with elementary matrices so far, maybe not. But I want to go over this again and sort of point out why we're doing this. There's a couple of reasons why, and a number of parts of this subject sort of come together with this idea of elementary matrix, right? So we turn to this definition right at the beginning on the top of the page here. It says, recall the row operation given in definition 1.11. And any elementary matrix, which we often denote by E, is obtained from applying one row operation to the identity matrix of same size, right? And you might be thinking, why, right? We have all of these different row operations that we apply to matrices. Why would we just care? Like, normally we're doing a bunch of row operations at once. So why would I care about this matrix that I'm just doing one row operation at a time? And let's go through. So they do explain it in this textbook, and it is worth reading through it, maybe after this live stream, if you've got some time, read through it again and read through their words and try and understand it in the way that they frame it. But let's go through a worked example. And again, please, I'll be checking the chat regularly, so please let me know if you have any questions. It might take me a second to see it because the current setup I have doesn't let me look at the chat at the same time. Unless, what if I did this? Haha. Yeah, I'm a genius. Okay. So let's look at an example. I think I've written down this this matrix before. It's like 1, 2, 3, 4, right? And we want to get this into reduced row echelon form, right? So let's go through and let's put it in reduced row echelon form. I see someone's here in the chat, so maybe can someone in the chat suggest a row operation we might do to try and turn this into reduced row echelon form? By the way, if anyone's listening, sometimes there's awkward pauses. because I might ask a question. To make it less awkward, I would like to put some gentle music on during the stream, but also some people that just doesn't work for. So I recommend, picking your favorite lo-fi chill hip hop beats on in the background for when there's silences. It'll make me seem less awkward. Unless you like me being awkward, then that's cool. So yeah, there's a suggestion: replace row 2 with row 1 minus 3 row 1. Yeah, that's a great idea, right? Because I want leading ones. I've already got a leading one here, so I may as well go and for reduced row echelon form, I need to make sure all the entries above and below my leading one are equal to 0. So I may as well knock out this other entry, and I can do that by going row 2. I should write row 2 becomes row 2 minus 3 row 1. So I'm going to get the matrix. Well, nothing's happening to row 1. Now row 3, or sorry, row 2, right? I'm going to get 1. I have 3 minus 3 times 1 is 0. I have 4 minus 2 times 3. Well, 2 times 3 is 6. So that's 4 minus 6. And I get a minus 2 here. Yep. And what else could I do? I've got my leading one. I've got zeros above and below. Well, I mean, there's no rows above my leading one. So now I look to my next entry, right? This is my leading entry. And there's two things I could do here, right? So there's normally different orders, different ways that we can come to this solution. And one thing I would do, because these two numbers are the same already, and because I have a 0 here, I know that this entry is not going to affect anything in the first row. I would go with something like row 1 becomes row 1 plus row 2. Now, the reason being is I haven't made my leading entry a 1 yet. That's true. But I'm sort of using this easy form. I notice I have 2 up above and minus 2 here and a 0 here. So if I add those rows, I'm using the fact that I can easily knock out this 2 in just one step here. And now I have this minus 2. And then, of course, we can see that the final operation here would be to divide the last row by 2. Right. So this is part, the process we go through to get to reduced row echelon form. But now let's consider the elementary matrix, right? So if I take, let's apply each of these row operations. So maybe I'll call this little a, I'll call this one little b. And then the last row operation we can see would be to go row 2 multiplied by 1 over negative 2 times row 2. So I'll call this operation C. And let's make the elementary matrices corresponding to these row operations. So for example, right, so if I applied just this one row operation to the identity matrix, right? So the identity matrix, the 2 by 2 identity matrix is just 1, 0, 0, 1. And so if I apply A to it, then what I'm going to get is, so row 1 is staying the same here. And row 2 is going to become a minus 3 times row 1. So I'm going to get a 3 times 1 here. Well, I'm subtracting it, right? So minus 3 times 1. So I'm going to get a 3 here. And then minus 3 times 0 is 0. So this is just the elementary matrix here. And now what I'm going to do is I'm going to multiply. So here's the elementary matrix I have corresponding to this row operation. And now I'm going to multiply the matrix I started with. So here in this example, we're going to get some good practice with matrix multiplication as well. I'm going to multiply these two matrices together. So here I'm going to, right, the first thing I do is this is the first entry I want to figure out is the 1, 1 entry. So I'm going to multiply across the first row, and I'm going to multiply down the first column. So matching those up. So this becomes 1 times 1 plus 0 times 3. And then for the 1, 2 entry, again, I'm going to multiply across the first row, but now I'm going to multiply down the first column, or sorry, the second column. So this becomes 1 times 2 plus 0 times 4. Okay. And now if I want to figure out the 2, 1 entry, I multiply across the second row and down the first column. So I get minus 3 times 1 plus 1 times 3. And then finally, for the 2, 2 entry, I'm going to multiply across the bottom row and down the final column. So I'm going to get minus 3 multiplied by 2 plus 1 times 4. Okay, and let's simplify this. So in the first entry, I get 1 times 1 plus, well, 0 times 3 is 0, so that's just 1. Here I get 1 times 2 plus 0 times 4. Again, 0 times anything is 0, so this becomes 1, 2. I'll leave the comma out of here. Then in the 2, 1 entry, I'm going to get minus 3 plus 3 is 0. And in the final entry, I get minus 3 times 2 is negative 6, plus 1 times 4 is negative 2. And now look at this. Here's part of the point. This isn't a coincidence that this matrix is the exact same matrix I get from doing this row operation, right? These are equal. So I did both of these. I did this 2 separate ways, right? One way I got from this matrix to this matrix by doing the thing that we're used to doing, and that is just applying this simple row operation. But now I have another way to view the world, right? The other way to view it is I can do it by applying this first, getting the elementary matrix that corresponds to applying that row operation, and then carrying this out by doing matrix multiplication. So I hope that makes some sense if that basic idea wasn't making a ton of sense before. But now the question might be, you might be thinking, well, okay, great. There's 2 different ways to do this, but why would we care, right? It seems like doing the row operation is a lot easier than having to do the row operation on a different matrix and then multiplying those matrices together, right? So there is actually a good reason, but let me first give you a little bit of homework. Is check these. Check that this also works for steps B and C. Right? So what I mean by this is take this row operation and apply it to the identity matrix. And so what will that give you, right? So if we look back at our identity matrix, row 1 plus row 2 is 1, 1. Row 2 stays the same. And you multiply it with the matrix that we're at now. 1, 2, 0, minus 2. And you should check. You should check that this is the matrix that we get when we're done, right? You shouldn't just believe me because I'm telling you this. You should check that practice doing the matrix multiplication. Check that this works. And then I'll for part C, I'll let you figure out what the corresponding elementary matrix should look like. And then, of course, if you're tuning into next week's stream and you're like, oh, I thought about this all week and I don't think I got it right. Well, we can talk about it on next week's stream. Okay. But I want to tell you the point, right? I need to tell you why would we care about representing these row operations as elementary matrices, right? So recall the definition of an inverse, right? These are really useful for helping us solve linear systems of equations. And in fact, they're going to be useful for a whole bunch of stuff later on, right? So a matrix, say big X, has an inverse if there exists a matrix, let's call it capital M, just because I need some letter, such that X times M is equal to the identity matrix. So X in this case has to be a square matrix. It has to be an n by n matrix. And in this case, M also has to be n by n. And so we usually write, right, if this matrix exists, we usually write M as X minus 1, right? So the suggestion here, the thing is, there's no such thing as dividing by matrices. But the reason why we use this notation is if we think about like just for numbers, what does it mean for a number to have an inverse, right? That means that for all numbers, right? Well, we know as long as X is not equal to 0, right? Because we're not allowed to divide by 0. As long as X, where here X is just some real number, if it's not equal to 0, then I know that X divided by X is equal to 1, right? Another way I can write this out, if you remember some of your exponent laws, well, first I can write this as the product of X times 1 over X being equal to 1. And if you remember some of your old exponent laws, if you don't, it could be worth reviewing them. I can rewrite 1 over X as X to the power of minus 1. Right? And now we have something, right? We have something that looks a lot like our equation for matrices, right? So again, we can't interpret a matrix X over 1 as being 1 over X, right? This doesn't make sense. We can't define division by matrices in general, but we can still have this idea of multiplying by an inverse to get an identity, right? And so the difference here, though, right, is there's just one exception in this case of real numbers, right? Because we want to be able to have these inverses in order to help us, solve problems if we're isolating for variables or something. And we can't always divide, right? We can't always have this this inverse. But here it wasn't so bad because there's just one special case that inverses don't exist. However, now for matrices, there are many which don't have an inverse. Right, so there's lots and lots of matrices I can write down that don't have inverses, right? All right, just checking my stream here. So, for example, this matrix 1 0 0 0 does not have an inverse. The matrix 0 2 0 4 does not have an inverse. What else I could do? 1 0 0 3, 0, negative 3, 9, 0, negative 9. None of these have inverses. But if a matrix does have an inverse, right? So the point is to remember, so a matrix doesn't always have an inverse, but if it does, this is what it means. We can find some matrix that we can multiply it by to get the identity. And the other thing to keep in mind, matrix multiplication is not always commutative, right? It's not always true that A times B is equal to B times A, but it is sometimes true. And when we have an inverse, that's one of the cases when it's true. X times X inverse and X inverse times X, those will always be the same thing, which is the identity. Okay, so let's think about what I've mentioned in the above, right? So all row operations can be encoded as matrix multiplication. So what that means is, let's suppose I have some matrix A, right? So say I've got some matrix A, and let's say, right, A is an n by n matrix, and let's say it's reduced row echelon form matrix is the n by n identity. Which I'll write as I, right? Oh, hey, so I've got more people in the chat. How's it going? We're just talking about matrix inverses right now and why elementary matrices help us solve matrix inverses. Right. So all row operations can be encoded as matrix multiplication. And so suppose I've got some matrix A, and let's say that its reduced row echelon form is the identity matrix, right? So what that means is I can find a series of row operations, right? So that means I can apply. And don't worry, if what I'm about to say seems sort of abstract, I'm going to go back up and we're going to take our example from earlier and we're going to see things a bit more concretely. So that means if I can apply a series of row operations, which maybe I'll use the notation O for row operation. So there's some row operation 1, O1, some row operation O2, up to, I'll call it On, to get I from A. So if I can get the identity matrix from A, right? But as we talked about up top, right? Each elementary row operation can actually be expressed as multiplication by some elementary matrix, right? And where we write the multiplication here, and then the result is on the right here. So in other words, that means that there also exists elementary matrices. So we'll just call them, say, E1, E2, ... right? En, where there's one for each of the row operations that we used, right? So if we, for example, if we applied the row operation O1 to, like we did this to our matrix A, then there exists, some elementary matrix E1, so that if I multiplied A by E1, I would get the result of applying this row operation, right? And then if I now took this and I applied O2 to this new matrix that I applied the elementary row operation O1 to A, well, I'm saying that there also, by everything I said above, there should also be an elementary matrix where I can now apply this new matrix that I got, right? This E1A, where again, now I should be able to multiply that by some other elementary matrix in order to get that same result. Okay, so this, I realize this is maybe seemingly a little bit abstract, but again, hold on a second. Just bear with me for a couple more moments. We'll do something more concrete. So if we're saying, right, if we're saying that I can apply all these row operations, so like I do the nth row operation to the n-1 row operation to ... and I do all these row operations, O2, O1, I do all these row operations to A, and I'm saying that I get the identity matrix, right? That's what I'm saying. Let's pretend that A's reduced row echelon form matrix is the identity matrix. So I apply all these row operations to A, but then that also means I can find n elementary matrices so that if I do this multiplication, I go En times En-1 times times ... down to E2 times E1 times A, that this is equal to the identity, right? But what does that mean? These are all matrices, right? I've got n matrices here. So if I simply multiplied each of these matrices together, then I would get one single matrix, right? If I just multiply, if I multiply En with En-1, and then I multiply that with En-2, and I keep going all the way down to E1, yeah, as someone just mentioned in the chat, that means that that A is invertible, that there is a matrix here that I can multiply with A on the left that results in the identity matrix. In other words, En times En-1 times ... down to E2, E1, this is a inverse. But okay, so this is all like kind of abstract and symbols, whatever. Let's look at our concrete example, right? So above, we were looking at the matrix A, 1, 2, 3, 4. It's just my favorite matrix to write down because it's an invertible matrix and it's just like the numbers 1 to 4 in order. And then what were our row operations, right? So we had so we were able to get this into reduced row echelon form. And the row operations we did is first we did row 1 minus so row 2, sorry, row 2 goes to row 2 minus 3 row 1. Then we applied row 1 goes to row 1 plus row 2. And then we applied row 2 goes to negative 1/2 row 2, right? So another way to look at what that means is, so if what I just told you above is true, right? If what I just told you above is true, then we should be able to find a bunch of matrices that if we multiply them together, it will give us A inverse. And even better than, oh, there's just some matrices out there that exist, we know exactly what those matrices should be. So E1 should be the matrix of the first row operation that we applied to the identity, right? So in this case, our identity matrix is 1, 0, 0, 1. So in this case, E1 should be, now we apply this first row operation to our identity matrix. And this is something we did above earlier. So row 1 stays the same. Row 2 will be -3, 1. Then E2 should be the second row operation applied to the identity matrix. So now row 1, we're going to add row 2 to it. So this is going to be 1, 1, 0, 1, because row 2 is staying the same. And finally, we should apply E3, will just be the matrix that we get applying the third row operation to the identity matrix. So this would just be multiplying. Oops, I almost wrote something wrong there. So this would be multiplying row 2 by -1/2. And so so if I'm right, if what I told you, if I haven't been lying to you this whole time, then it should be true that E3 times E2 times E1, and remember the order that you put them in is important because matrix multiplication, so you could write A either on the left or the right of the E's, but you can't mix up the orders of the E's necessarily. Wait, is that even true? You might be able to mix up the order of the E's. But for now, let's just not, because the matrix multiplication, you can't always do it, right? Only in special cases. So what if so what I'm telling you, if this is true, we should be able to write these matrices in, right? So here's E3, here's E2, and here is, oh, I wrote it backwards. Sorry, E3 is the last one that I wrote down. So that is 1, 0, 0, -1/2. Then I have E2, then I have E1. And if what I'm saying is true, if we multiply these things together, then if I multiply all of these by A, I should get the identity matrix. So in other words, I'm just going to quickly, so normally you probably know by now, I like to go through these steps really slowly and explain everything I'm doing. I'm just going to multiply one of this out really quickly because I want to give you the answer, and then I want you to try this on your own afterwards, and actually go through the steps and check. But I mean, if you can follow what I'm about to do, that is also great. So first, so I'm just looking at these matrices here. I'm going to multiply these two matrices together first. So this is going to be 1 minus 3 is -2. 1 minus 3 and 1. And then multiplying these two matrices together, I should get -2, 1, 3/2, and -1/2. Assuming I didn't make any mistakes in my arithmetic. So the point is, right, if I combine all of these matrix multiplications together, then this is the matrix that should be A inverse. And check this. Again, if you do try this over the week and you're just not, it's just not clicking for you, of course, you can ask me in the live stream next week. We'll solve some questions together. And yeah, I mean, sometimes I make small calculation errors too. So you may not just be losing your mind. I might have just made a small mistake. But this is good homework to check this, right? So in summary, part of the reason why we care about elementary matrices is because it gives us an easy way to find the inverse of a matrix. And this is the whole idea behind. So one way to do it is that as we've seen, you know, if the reduced row echelon form of a matrix is the identity, then we can just the inverse of that matrix will just be the result of multiplying all the matrices of the corresponding row operations together. But that's also a lot of work, because first you're reducing a matrix to like reduced row echelon form, especially like if these are 3 by 3 or even larger matrices, there's, you know, that's a lot of matrix multiplication, especially if there's a lot of steps, right? And so there is a quicker way to do it. I don't know if I'm going to explain in detail today why this works. I think it might be better to move on to just solving more, you know, explicit problems, maybe from the textbook or something. But this is where this method, so hopefully you've seen this. So if you have a matrix A and you set up, so A, of course, again, has to be n by n. And you set up the augmented matrix where you put on the right the entire n by n identity matrix. Then if you turn this, if the reduced row echelon form, I'm not saying it will always be, right? Like some matrices, the reduced row echelon form is not the identity. But I'm saying if it is, then the reduced row echelon form, once it is the identity, then whatever matrix you have sitting on the right is going to be your inverse. And it basically comes from this idea of the elementary matrices and row operations being the same thing, right? So in the example I gave you above, I basically showed you how to get from row ops to elementary matrix multiplication. But the method I just mentioned below basically does the other thing, right? It says, let's suppose A inverse existed, you know, break that product up into elementary matrices, and then go backwards to your row operations. But that's just the the sort of vague, intuitive explanation for now about why this method works and why this helps us quickly find the inverse. But remember, if, right, so maybe I should, just to be extra clear, I should put a warning here. If the ref of A is not I, then A is not invertible. Right? In other words, A inverse does not exist. Yeah. Oh, where'd I put my water? So, and this basically, again, this boils down to more or less the same argument we made above about the elementary matrices, right? So if, because all the row operations can be formulated as matrix multiplication, right? It says if you can find row operations that turns your matrix into the identity when you multiply it by something, then that means you can actually find matrices to multiply your matrix by in order to get the identity. So if we can't find row operations that turns our matrix into the identity, right, when it's in reduced row echelon form, then that means that we also can't find matrices to multiply it by on the left that gives us the identity matrix, which is basically what it means to not be invertible. So I think that's all I'm going to say about invertibility and elementary matrices for now. I think I'm going to move on to determinants. Of course, you know, if anyone has any questions in the chat, you know, let me know. We can talk more about this or something else specific from the course if you want. But I think it's good to go into detail about determinants of matrices. So why don't we move on to determinants then? And I don't know where you've been in your course so far, but this might be a little bit of a spoiler. So spoiler alert, warning, if you like following along in your class, I'm going to tell you something. I'm going to spoil something. Well, I think it's neat about determinants, and that is determinants help you figure out if inverses exist. Now, one thing I want to remind you about, so we haven't really talked about vectors and vector spaces if you're following this course yet. But once we do, I would really, really recommend 3 Blue, 1 Brown on their channel. They have, I'll try and remember to put a link in the description. They have specifically a series called The Essence of Linear Algebra, and it doesn't help with, there's not a lot of like very explicit worked examples, but it has a lot of nice animations, and it sort of explains like why things are true and what they mean. Like all this stuff, like it's not just mathematicians being like, oh, let's like write some numbers down or something. It all means something. It has like, there's physical meaning, right? This stuff lets us do physics and computer science and even biology, right? And so there's a neat video in that playlist that talks about the determinant and the geometric meaning of the determinant. So I would highly recommend checking out this channel. Although he does go into like vectors and vector spaces, which we haven't covered yet. And just warning, yeah, that some of that will be new information. But once you see it, it's like, it makes all these things click together. Okay, so what do I mean by determinants help you figure out if inverse exists? Well, this is just what mathematicians would call a theorem. So this is a fact that one can prove beyond a shadow of a doubt. Is that for any n by n matrix, A has an inverse if and only if, and sometimes mathematicians, we like to be lazy, and we'll abbreviate if and only if by writing IFF. So just a bit of notation I want to warn you about, because sometimes I forget that not everyone knows that, and then I like slip into this bit of notation. But again, if I say something that doesn't make sense, please let me know in the chat. So if A has an inverse, A has an inverse if and only if the determinant of A is not equal to 0. Right? This is the spoiler alert. Sorry to ruin the surprise of this, but that is, I want to give you some of the motivation, so you can see that it's not always total just random chaos, right? Like this all comes back to solving linear systems of equations, right? So we saw row operations help us solve these linear systems of equations. But then there's certain problems where it's actually easier if you know whether or not an inverse exists. And then, well, so it might be nice to have like a quick way to figure out if inverses exist or not. And so the determinant helps do that because of this rule here, right? So the if and only if, that means that, number one, if A has a non-zero determinant, So if it's any number not equal to 0, then you know the inverse exists, guaranteed. But then number 2, it tells you a second piece of information, which is slightly different. It tells you that if it's not equal to 0, then definitely guaranteed it does not have an inverse. You'll never be able to find an inverse matrix for it. So, I mean, let's take a look at an example. The 2x2 matrix above, right? So if what I'm saying is true, like whenever you learn about one of these theorems or facts in class, you should put your skeptical hat on, right? You should think, okay, why should I believe that? Why is that true? And what you should do is write down an example, right? Just like write down a rando 2x2 matrix. And I mean, this is a great way for you to also get practice just using all the concepts in class, right? So if someone tells you, oh yeah, a matrix has an inverse if and only if the determinant is equal to 0, well then go and try and write down a couple 2x2 matrices. Hopefully you find one or two that is invertible or is not, right? A 2x2 matrix won't take you too much time to play around with that, turn into reduced row echelon form, right? And then, so find out if it's invertible or not, and then check what its determinant is, and see if that matches up with what the theorem is telling you. And then a good check to make sure, if you find something that contradicts what the theorem says, then you know that you either need to check your work and your understanding, or maybe the theorem's wrong. Although if it's in a linear algebra textbook, the theorem's probably not wrong. It's definitely not wrong in this case. So let's compute the determinant of this. And so as I've said before, there's you don't want to just memorize everything. You want to understand stuff, but there are some things you need to memorize. And I would definitely memorize the formula for the determinant of a 2x2 matrix. Right? Always, 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 if you have a 2x2 matrix, the determinant is A times D minus B times C. And there's a bit of a pattern here that we're going to see generalizes. This will be useful in a moment when I'm going to tell you a trick for 3x3 matrices in case you haven't heard this one yet. But so I always think of going down and to the right as adding and down and to the left as subtracting. And this is a pattern. It gets more complicated, but it continues over to 3x3 matrices. So here we have, right? First we do down and to the left, we get A times D, and then down and to the right is negative, so minus B times C. So let's check, right? Let's check our formula. So the determinant of this matrix, according to our formula, should be down and to the right, which is 1 times 4, minus down and to the left, which is 2 times 3. Well, 1 times 4 is 4, 2 times 3 is 6, 4 minus 6 is minus 2. And yeah, that's not equal to 0, right? And that's exactly what this theorem told us we should expect to be true, right? If A has an inverse, it does. We found an inverse for it up above. Then the determinant should not be equal to 0. And it's not. So great. Seems like this thing is true, right? Of course, mathematicians, you shouldn't really trust anything until you've seen the proof. Although in this course, there just isn't time to prove things and learn how to prove things. But that is the ultimate way that we know these things are true. But it's also good to just double check these from time to time. So let's talk about the determinant of a 3x3 matrix. So probably you've already seen cofactor expansion. And maybe before we're done today, we'll go through an example of cofactor expansion. But so it's like, there's lots of worked examples in the textbook. Still, wouldn't hurt us to do one together. Cofactor expansion is great for 3x3, definitely 4x4, 5x5. All these things, cofactor expansion is great, and there's like strategies to like use it smartly. But for 3x3 matrices, I mean, you can use it and it's totally fine. But there's a way that I like to think about 3x3 matrices and their determinants, and that I just think it's nicer for me to think about. And so I'll write down a particular matrix, but this general pattern generalizes for any 3x3 matrix. So maybe we'll go like 1, 2, -1, 0, 3, 2, -5, 1, -2. And we want to figure out what the determinant of this is. And so the thing is, like, the determinant is the determinant. It's always going to be the same no matter what method you use to compute it. So the answer we should get from this is going to be the same thing that we get from cofactor expansion. But I like this method. So what we do is we're going to copy the first two rows. So if I want to calculate, I guess I should write determinant here just to not confuse anyone. So what we're going to do is copy the first two columns, right? So I look at this first column, 1, 0, 5, 1, 0, -5. I'm going to copy that down. And then I'm going to copy down column 2. And what I'm going to do now is this same pattern where I multiply down and to the right with positives. And let me pick out a red here. And I multiply down and to the left with negatives. So what this looks like in the 3x3 case, however, is, so I multiply down this way. So I'm going to get 1 times 3 times -2, right? And so positive out in front. So plus 1 times 2. And now this is why this other column is here. I know this isn't a very good explanation of why this works. And maybe next week's live stream, I'll explain more why it's true, because it's important to know that. But right now, I just want to teach you this method because it's a good, fast trick. If it works for you, it's a good, quick trick for exams and stuff. So now we get 2 times 2 times -5. And then multiplying down to the right again, we get plus -1 times 0 times 1. I'm just checking on the stream. Okay. And then, like I said before, we multiply down and to the left with negatives. So I'm going to multiply down and to the left here, but I'm going to put a minus sign out in front of each of these terms. So I start with minus, and I have to be careful here because there's two minus signs, right? I have a -1 here, so I need to make sure that negative is still attached to that 1. So -1 times 3 times -5. And then down and to the left. So again, I put a minus sign in front, and it's going to be 1 times 2 times 1. And then finally down and to left, so minus sign 2 times 0 times -2. And now I can just simplify these calculations, right? So multiplying by 1 doesn't do too much. Here I get -2 times 3 is -6. 2 times 2 is 4. Multiplied by -5 is -20. And then this has a 0 on the multiplication, so that's just not going to appear. -1 times, I've got -1 is just +1. 3 times -5 is -15. -1 times 1 times 2 is -2. And this term has a 0 in it, so it just doesn't appear there. Then what do we have here? So -20 and 15 is -35. -6 is -41. -2 is -43. And so, okay, so we found the determinant of this matrix. And notice this was, you'll probably notice if you've done cofactor expansion on 3x3 matrices, this is probably a lot faster of a method. So let me just write out the general rule for you in a more abstract notation, in case that's helpful. I realize for some people it may be less helpful. But the general rule is if you have a 3x3 matrix, which is A, B, C, D, E, F, G, H, I, then the way that you can compute the way the trick works for this determinant is, again, you write the first column and the second column again, and you simply go, oh, it's not the color I wanted to use. So you simply add down and to the right. So that means we get A times E times I plus B times F times G plus C times D times H. And we multiply down and to the left, which means we get negative C times E times G, negative A times F times H, and negative B times D times I. And you can go ahead and check if you use, say, cofactor expansion. Like if you were to write out cofactor expansion of this abstract matrix of symbols, you should find this should be your final answer, right? I mean, you might end up writing some of these in the opposite order, like E times I times A, but remember, these are just numbers now, so that would be like the same thing as this term. So in fact, we're nearing the end of the hour here. So if anyone has some questions, feel free to ask. But here's another good piece of homework. Is do this, right? Do this cofactor expansion just with this matrix with these arbitrary variables, right? And there's nothing else you have to do different here, right? We're just pretending that these are numbers, right? These are just name holders for numbers. So you just pick any row you want to do cofactor expansion along it and just do cofactor expansion. And in order to check that you did it right, it should be equal to this at the end of it. But so this is the right, in both cases, it's the same sort of pattern that we're using to determine the determinant of a 3x3 matrix. So this is a great way. You're going to need to know all the methods for course, but if they just tell you, find the 3x3 matrix, or say like just determine, just figure it out if it's invertible, this is a great way to use the determinant quickly. And so that's maybe, I guess I gave you one homework above was to multiply some matrices together. So I'll say this is homework problem 2. And again, yeah, if you get stuck, like ask me in next week's live stream. And then homework 3 is, so let me write homework 3 is, well, we found the determinant of this matrix, right? And we figured out that its determinant was minus 43. And what did I tell you? I told you this fact. I said that a matrix has an inverse if and only if its determinant is not equal to 0, right? So minus 43 is not equal to 0. So if what I said is true, then this matrix should have an inverse. So homework 3 is find the inverse. And we have a method for doing this. I mentioned earlier in class, right? If we take a matrix A, we set up the augmented matrix so that the identity matrix is on the right. If we're able to get it into reduced row echelon form on the left, then we know that the matrix on the right is A inverse. And what I've just told you, right? What I've just told you is that this matrix is invertible. That's what we found out together just now. So we should be able to do this, and we should be able to determine its inverse. And then finally, let me even give you one more piece of homework. And the great thing about this is all of these you can check, right? So once you've found what you think is the inverse, is check it. Right, so maybe call this homework 3.5. Well, how can you do that if you don't have a professor or me sitting there and grading your work? Well, remember that in order to be an inverse, A times A inverse has to be the identity, or you can even switch the order in this very specific case if you want. So in other words, take this matrix A that we started with, multiply it by the inverse on either side, it doesn't matter, and check that you get the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah. Okay, well, it's been an hour. We've covered a lot of ground today. Yeah, perhaps I'll see a bunch of you next week. It's always most useful for you if you come armed with some questions. So yeah, thanks for watching, and take care.